Hello and welcome back to Circuit City. Today we'll be covering logical equivalence, which is very important for midterms and other examinations, so make sure to take notes. Here's a quick look at how we can use logical equivalence to our advantage. x1 plus x2 knotted, as we know through De Morgan's law, equals x1 knot times x2 knot. We can take advantage of this and other Boolean algebra laws to change our circuits in such a way that they're cheaper to produce. And we can make them cheaper by optimizing the number of transistors and the variation in the designs that they use. Generally speaking, less variation in a circuit means less cost when manufacturing. Below you see a circuit representation of De Morgan's law, specifically a representation where we change a NOR gate into two NOT gates and an AND gate. Generally speaking, when a company like Intel or Apple manufactures CPUs, they mostly use NOR and NAND gates. Let's quickly take a look at how many transistors it takes to manufacture some of the common gates that we've seen. For a NOT gate, it takes 1 transistor. For an AND gate, it takes 6 transistors. And for the NOR and NAND gates, it only takes 2 transistors. This is very useful as NOR and NAND gates can be used to build complicated logical circuits without the same cost of, say, an AND gate. This is something important to take note of, as a CPU such as the Apple M2 chip uses 20 billion transistors, so to optimize the number of logic gates and in turn transistors we need is very, very important when manufacturing CPUs. Let's take a look at some more examples of logical equivalence. As you can see, a NOT gate can be turned into a NAND or NOR gate simply by feeding the input twice to the NAND and NOR gate. And below, I'm also drawing how a NAND gate can be transformed into an OR gate with 2 complemented inputs. This is simply just the other version of De Morgan's law, which you saw previously. Now, you may be thinking, why would we ever want to change a NOT gate into a NOR or NAND gate? Well, as I mentioned previously, lack of variety in logical gates also influences the manufacturing costs. So, only having to manufacture using NAND and NOR gates can be more advantageous to producing a combination of, say, NOR gates and NOT gates. A quick exercise for you would be to prove that all these logical equivalences are actually true. For the NOT gate proofs, I would recommend using a truth table, and obviously the third one you can prove through De Morgan's law. Now let's get into some actual example problems. Describe the following using only NAND gates. I would like to point out that this is a sample midterm question, which I got from the ECE 124 course taught at the University of Waterloo. This was a question given to students in the spring 24 midterm. So, it says to describe the circuit using only NAND gates. How do we tackle this problem? Well, a good place to start might be to number off all of the inputs so we know exactly what we're inputting into our circuit. So I'll start by calling our logical function f, and I'll number off all of the inputs, x1, x2, x3, x4, x5, x6, and x7. Oh, that looks like a z. Quickly turn that into a 7. And so what we basically did here is we acknowledged that our circuit takes in 7 unique inputs and comes up with an output. Before we start, I'd like to show something kind of important when solving this type of problems. When you input x1 into 2 NOT gates, you end up getting x1 once again. And this is very, very important when doing problems like this. You'll see why very, very soon. With that being said, let's start to analyze our circuit and let's start creating our NAND gates. So starting off, we can add a NOT to the end of our AND gate and a NOT gate right after that to sort of keep the logic of the circuit the same. And I'm going to describe that NOT gate as sort of a complement at the bottom of my OR gate. You'll see why pretty soon. This will allow us to take advantage of De Morgan's law. Finally, I will add a complement at the very last AND gate and a NOT gate at the end of our circuit to keep the logic the same. Next, to allow us to use De Morgan's law on our OR gates, I will add another complement behind our OR gate, which takes in the input x7, and to keep the truth values the same, I will add a NOT gate to that input. I will do the same for the rest of the OR gates in our circuit. Alright, now we have a pretty good idea of what our circuit is going to look like. We know how to describe NOT gates using NAND gates, and we know that we can use De Morgan's law to turn our OR gates into NAND gates. So let's follow through and create our new circuit. I'll start with the input x1. We immediately see a NOT gate, and we can describe that as a NAND gate immediately. And moving on, we can use De Morgan's law on that OR gate to turn it into a NAND gate. And De Morgan's law is the only way to turn OR gates into NAND gates, as we know from Boolean algebra. I am going to number off our gates as to not lose track of them. So I'll call that NOT gate, gate 1, and that OR gate, gate 2. And I will call the gate that takes in x2 and x3 as gate 3. So let's quickly take in our inputs x2 and x3 and draw our third NAND gate, which will feed its output to gate 2. All right, nice. Now we have the upper portion of our circuit done, so we can get to work on the lower portion of our circuit. All right, a bit of camera magic to zoom out there. Let's take in our input x4 and draw our fourth NAND gate. I am going to label that as 4. And let's get to work on our inputs x5 and x6. We have NOT gates, which we can turn into NAND gates. So we will take that input, split it in half, and turn it into a NAND gate. I'm going to quickly copy that over. And here we are. We have 2 NAND gates to describe our 2 OR gates. So that is our 5th and 6th NAND gate. And those will be inputted into another NAND gate, which we transformed using De Morgan's law. All right, we have a few more gates to go, and then we're done. So that gets inputted into gate 4, as we see above in our picture. And now we can get to work on our final input, which is x7. Oh, that kind of looks like a Z again, whatever. So we have our 8th and 9th NAND gates here. So let's go ahead and quickly draw those. I will once again split the input, feed it into a smaller NAND gate because I did not leave enough space to draw this. And that will be one of the inputs to our 9th NAND gate, which I will then connect our 4th NAND gate to. And finally, we have our 10th and 11th NAND gate to complete our function. So our 10th NAND gate will take the input from the upper portion of our circuit there and the lower portion of our circuit from the 9th NAND gate. So that is our 10th NAND gate. And to simulate our NOT gate at the end there that we drew, we will split our input in half once again and draw our final NAND gate. Once again, I would like to emphasize that this is a very common midterm question, and I would highly recommend learning how to do this type of question. Thank you so much for listening and have a great day.